Okay, good morning, good afternoon, good evening, everyone from all over the world. My name is Cheung. I'm a research fellow at National University of Singapore. And today it's my great pleasure to introduce today's speaker, Dr. Mike Cheung, a full professor at the Department of Psychology at the National University of Singapore. When we sent out the survey to gather feedback on who to invite for the SRM-ASIC fall seminar, Dr. Cheung was the most popular choice. This really shows how much impact his work has in our community. Dr. Cheung is renowned in the field of quantitative methods with a specific focus on structural equation modeling, meta-analysis, and multi-level modeling. Dr. Cheung has made substantial contributions to the integration of meta-analysis and structural equation modeling. With over 80 articles published in prestigious international journals and a highly influential book titled Meta-Analysis, a Structural Equation Modeling Approach, Dr. Cheung has significantly advanced our understanding and application of these complex methodologies. Today, Dr. Cheung will be sharing insights on fitting flexible meta-analytic models with structural equation modeling. He will present for about 40 minutes, and feel free to raise questions throughout the presentation. Please feel free to leave your questions and thoughts in the chat during the presentation, and we'll make sure to address them during the discussion. Without further ado, please join me in welcoming Dr. Mike Cheung.
Thanks a lot. Good morning, good evening, good afternoon, depending where you are. And thanks again for the invitation and very nice introduction. Probably is too nice. Okay, so my name is Mike Cheung, and today's topic is about meta-analysis and structural equation model. So I've been started to work on this line of research since my postgraduate studies, my master PhD, and then in my career, I spent probably most of my time on this topic. So today, what I'm going to do is to talk about how to fit structural equation how to fit meta-analysis with structural equation models. Before that, I'm going to spend just one slide to summarize what's available in my package, metaSEM package. So this package, the metaSEM, uses structural equation models to conduct meta-analysis. So essentially, it uses the power of OpenMX and lavaan, and at the same time, it uses SEMplot for visualization. And among various functions, there are basically three groups of functions. The first one is to calculate effect sizes and their sampling covariance matrices. For example, we can use the mean covariances depending on the structures. Sometimes we may want to calculate some sort of crazy effect sizes. So as long as they can be framed as structural equation models, then these functions can help us to calculate the effect sizes and, more importantly, the sampling covariance matrices. And then the second group of function probably is the most important one, is the meta-SEM, Meta-Analytic Structural Equation Modeling. Most users, I think, when they use the meta-SEM package, basically, they are mainly interested in this area, because if you want to do conventional meta-analysis, probably MetaFort is the best package to go. And personally, when I do conventional meta-analysis, I also use MetaFort. But for some combination meta-analysis and SCM, like the meta-SEM, then this package provides two different sorts of functions. The first one is two-stage SCM. The second one is more recent development, is the one-stage meta-SEM with Suzanne Jack. And recently, we are working on a newer function, one-stage meta-SEM 2. So it provides analysis with covariance correlation matrices with means. So by adding the means, then we can analyze and ask some interesting questions. So Suzanne will have more details, hopefully a few months later. Then the last group of function is about the so-called SEM-based meta-analysis. So this is more like a conventional univariate, multivariate meta-analysis or three-level meta-analysis. And today, I'm going to focus on one particular new function, SEM. Okay, so this SEM function can be used to fit standard SEM models, but to us, probably we are more interested in meta-analysis. So what's the motivation behind the development of this SEM or the SEM-based meta-analysis? So the idea is if we want to learn meta-analysis, the conventional or the textbook way is to learn all of these mathematics, algorithms, estimation methods. But sometimes it will be challenging for users who are not that math oriented. Secondly, even though metaphor is very powerful, it can be used to fit lots of new models. But sometimes our research questions are so novel that no available methods are available. For example, we may want to fit regressions among the effect sizes or mediation models. And then today's talk is trying to fill these gaps by introducing a different way to learn, understand meta-analysis, and also to fit meta-analytic models. Okay, so it's all about meta-analysis and SEM. So the first example is just a standard random effects model. So in here, I highlight it. It's called additive heterogeneity. So the model is like this. So basically, we have a average effect, random effect, and sampling error. And then we assume the sampling variance is known, and then the heterogeneity tau squares. And then the so-called fixed effects or common effects model is a special case when the tau square is 0. Okay, so for those who don't like the math, so let's use this model. Okay, so this graphical representation is a structural equation model, but at the same time, it represents a random effects model. So first of all, let's look at all of these symbols one by one. The first one is this rectangle yi. Obviously, this is an effect size, so it can be a correlation coefficient, a standardized mean difference, or whatever effect size. And then we have a triangle with a 1. So this is mean. It represents the means or intercept, and then it's pointed towards this yi, and then it's labeled as the mu. So this is the mean of these average effects. Okay, so we have the average effects here. On the left-hand side, we can see two circles. They represent latent variables. The first one on the top, UI, is the random effects. So this is like the traditional random effects model with a mean of 0, and at the same time, the variance is tau squares. So, and then it's added towards or observed effect size. Okay, and on the lower part here, we have a sampling error, EI. Okay, and in here, one interesting notation is the data.vi. So probably many of us know what VI is, especially meta-analysis. VI is the known sampling variance. In here, we use the OpenMX notation by using data.vi, meaning we assign each participant or each study in meta-analysis to this particular variance. In other words, if we have 10 studies, then these 10 studies have 10 different VI. Okay, so when we fit this model, in here there are two parameters, two unknown parameters. The first one is tau squares, the heterogeneity, and the second one is mu, the population variance. Okay, and based on this model, we can calculate what we mean model-implied matrices. The mean structure is just the average, the mean. And then the variance structure is the tau square plus the VR. So it's quite similar. In fact, it's identical to what I've learned in meta-analysis. Okay. But if we're using a structural equation modeling approach, then what we need to do is just to specify this model. And then the programs in R will help us to translate them into the model-implied covariance structure and fit the data. And let's introduce slightly more complicated models. So the additive heterogeneity, the standard random effects model, is not the only model available. In the literature, some researchers have proposed some alternatives. For example, model with multiplicative heterogeneity. So under this model, there's no tau squares, okay? But the sampling variance, the known sampling variance, is scaled by a scaling factor of phi, okay? So this phi, if it is 1, then it's the same as the fixed effects or common effects model. But usually if the estimated phi is larger than 1, then the standard error would be larger than the conventional fixed effects models. So how to specify this model in SEM? So basically it's the same, but now the factor loading is we use the phi, the square root of phi. Okay, so why we use the square root of phi instead of phi? So let's look at the model-implied matrices. Then it make it obvious. The mu is the population mean. Okay, but for the variance structure, since the factor loading, when we write it in terms of variance structure, we square it. So now it is the phi vi. So this follows the standard convention under the multiplicative models. Okay, then how about the best of both worlds? So additive plus multiplicative model. Yes, we can do it. In fact, when I reviewed the literature, I found that there are at least 3 different types of hybrid models combining both additive and multiplicative models. And in the preprint that I'm going to show the link later, you can go to it to read more about these alternative hybrid models, including both additive and multiplicative models. But from a graphical or SEM perspective, it's quite straightforward. Now we have a random effects. Okay, so additive tau squares, so we add it here. At the same time, we also try to scale the known sampling variance with the square root of the tau squares. And based on this model, then we can have the model-implied covariance matrix. As we can expect, it's a combination of both the tau squares and phi. Okay, and I hope these 2 examples can provide you some ideas how we are going to use this SEM approach. Basically, when you have some ideas, then you can write them as graphical models. But by the way, what we are going to do is write them in equations, and then we can translate the models into different forms of representation for analysis. Okay. But in principle, there's no restriction what models we can fit. Okay. For example, if you have multiple effect sizes, then we can also allow some of the residuals or the random effects to be correlated. So in the later examples, we also have a bivariate meta-analysis. Okay, and now we can put all of these 4 models here. So fixed effects model, a random effects model with multiplicative error, and hybrid models. And instead of presenting equations, then now we can easily see what are the differences and implications. And there's almost one-to-one correspondence between the models, assumptions, and also the graphical models. So it makes it easier for users or learners to understand what models we are fitting instead of using lots of statistics. Okay, so what's the actual way to run the analysis in R? So this is the typical workflow. First, we specify the model in equations. Okay, then we can optionally to generate conceptual graphical models to understand what model we are going to fit. But this is not necessarily optional. The next step is to convert it into RAM specification. So if you are new to SEM, then even I think many SEM users, they may not know what the RAM specification is. Internally, most SEM packages, they use matrices to represent the models. So we can translate the equations into this RAM. So for us, we are not interested in the RAM specification, but it's an internal representation for these R functions. So that's why we need it. Then optionally, we can get the model-implied matrices like the mean and covariances. And I found this function quite helpful because in terms of graphical models, there may be multiple versions of the same models, but after getting the model-implied mean and covariances, then we may find they are identical. So this also helps us to understand what models we are actually fitting. Then this part probably is the most important part. That is, after proposing the model, we can feed them to our data. Okay, and then optionally, we can also plot the results. So let's go to an example to see how it works. So these examples, the effect size is a correlation coefficient between organization commitment and sales person jobs performance. To simplify, we call it YI as effect size, and then we have calculated its sampling variance. And at the same time, we use the individualism scores of the studies as a potential covariance we call XI. Okay, so these are the R codes. Like first we load these two libraries, and secondly we prepare the data. Okay, so just a standard procedures. Okay, and now here's the sample data for the first 6 rows. So YI, VI, and XI. So we use XI only if we are fitting a meta-regressions later. Okay, so let's try to fit hybrid model. So I think this hybrid model is complex enough to demonstrate what this SEM approach can be used. Okay, so it uses the lavaan syntax to specify model. So in lavaan syntax, we use a string in R to specify, and some of this, the lavaan syntax is an expanded version of the linear model in R. So probably some of you, if you are familiar with linear regression, the LM function, then you notice this one represent YI is modeled by an intercept. So we label the intercept mu. So this is the average effect. So in other words, we tell the SEM program that we call the mean, the average effect mu. Okay, and then by default, there's a measurement errors, okay, between all observed effects, and these measurement errors can be used to represent sampling error. But since we are going to use the E, another latent variable, to represent it, then we just set the measurement error, the variance of it, as 0. Okay, so now we add the additive error, the heterogeneity, the tau squares. So these two lines, the first one we define a latent variable UI representing the additive random effect, and then we label its variance. The double tilted represent variance. Okay, so it can be any names. We just call it tau squares to make it easier to follow. Then now for the known sampling variance, we got EI. Okay, and then we call the loading, factor loading, phi square root, and then we assign the variance as a known data.vi, meaning for each studies, it has its own VI. Okay, and one interesting application or use case is in SEM, we can, especially lavaan or OpenMX, we can define a new function of parameters. For example, in here, the phi square root is the parameter. But I like to interpret the phi instead of the phi square root. So now I'm using this line. So colon equal, meaning I define a new function of parameter phi, which is the square root of the phi square root. Then basically, it turns out it's just phi. Okay, so after run the analysis, the programs will give us the phi square root and also the phi at the same time. So in other words, it's very useful for this trick. We can use it to define lots of useful things like the R squares. Okay, and by the way, in SEM, as long as the labels are the same, then they will be constrained equally. For example, if later when we have bivariate meta-analysis, if you want to test whether the means are the same, instead of using mu1 and mu2 for the first and the second effect sizes, we can just call them mu. Then they will be constrained equally. Then we can test whether they're the same or not. So after specifying the model, then this is optional. We can plot this model. So it gives us a graphical representation. So it's very helpful because it reminds us whether this is the model, what we would like to fit. Okay, and there are solid lines and fixed lines. For the fixed lines, it means that the parameters are fixed either as any values. In this case, the mean here for this part it is 0. For the mean, it's also 0 because they're random effects. Okay, and here the mean of the yi is mu. So this is the parameter. So in here, we have 3 parameters, 3 unknown we would like to estimate because the data vi, it is known because just like meta-analysis, okay? So then we can convert it into RAM representations. So with this command, and I've also mentioned this function before, implied. So I can use it, then we can calculate the model implied mean. So we can see this is mu, and also the model implied covariance matrix. This is the tau squares plus the vi time phi. So this is exactly the same as the models we are talking about for the hybrid model. So we know we are fitting the correct model. Then the most important step is to fit it against the data. So we have the data, in our case, is under DAT. Okay, and in here, I'd like to get Lyco-based content interval. So in here, if we don't specify this argument, then the standard content interval would be based on the z-test or what-test. Okay. And if we specify it, then we can get the Lyco-based content interval. Okay, so then these are the standard output. Okay, so the parameter estimate of mu, the average effect, and then the phi square root and the tau squares. Okay, and then the lower bound, upper bound, and more interestingly, we can also get the phi. If you still remember, we have defined the phi equals the phi square root, the square of it. So it helps us to calculate the Lyco-based content interval of any functions like this one. Then we can interpret. Then we don't need to manually convert it. So that would be useful if we have, let's say, log ox. But after analysis, we would like to get the ox ratio instead of the log ox. Then finally, we can also plot the results just like this one. Then we can have a visual representation of hybrid meta-analysis. So the average effect is 0.1874 in terms of cohesion coefficient. And then the tau squares, the additive part is tau squares 0.01. And then the scaling factor, the square root is 1.28. Okay. So this gives a very different perspectives if you're teaching, let's say, meta-analysis instead of using all of these equations. Then now we can have some figures, graphs to show to the readers, to the students what model is and what are the conceptualization. Okay, so then we can also compare all of these 4 models. So the hybrid model, random effects model, multiplicative error model, and the fixed effects model with AIC. So just look at the AIC of this model. In terms of AIC, the smaller is better. Okay, so we can see for the fixed effects model, the AIC is quite huge when comparing to others, meaning the fixed effects model is the worst model. But for the others, the hybrid model and then the random effects model, the AIC are more or less the same, meaning the model fit are quite similar. We can't tell which one is better. But for the multiplicative error model, is slightly worse than a hybrid and random effects model. Okay. So we can use some of them when they are nested. Then we can use chi-square difference test, also known as likelihood ratio test, to test them, or we can use AIC, BIC to compare the models. Okay, so before moving to other topics, any questions right now? Anything you'd like to clarify? Okay, good. So, yes.
Can I ask a question?
Yes, sure.
So you showed that you can do like reparameterization of the variance parameters. Can you put models on the variance? Like, could you, like a location scale model?
Yeah, so good question. Don't worry, I'll have an examples using location scale model. So
Oh,
probably
okay.
at that, thanks. I think, yeah, so that one probably is more interesting.
Okay.
Thanks. So we'll go back to the location scale model later. Okay, then let's move on. So suppose now we have the predictor. So we can conduct a meta regression. So basically, this is a mixed effects model. So this model is quite standard. Okay, and in meta-analysis, the predictors are usually considered as fixed or design matrix. So we call it a fixed X approach. So in here, under this model, so essentially it's more or less the same. So we have a random effect, the random effects, non-sampling variance. But on the mean, instead of just the beta naught, the F, we need to consider the data xi. In our case, is individualism. So in here, we use a phantom variable, so the eta. So the meaning of phantom variable is a latent variable, but without variance. Okay, so basically it's just like a placeholder to help us to identify this path. So let's go back to the model-implied covariance matrix. After specifying this model, then the mean of this model becomes the beta naught plus beta 1 times the xi. Okay, so the xi varies across different studies. In other words, this mean this mu I also varies across it. And the variance structure is essentially the same as the random effects model, except that now the tau square is the residual heterogeneity. Okay. So this is the standard meta-analysis in regression and meta-analysis. Okay. But in SEM, they also have a slightly different flavor. They like to treat the predictors as random variables. So this is called a random X approach. Okay, so there are pros and cons of this approach. The main advantage is it can handle missing predictors with full information maximum likelihood. So it's quite effective and efficient. But the limitation is now, since the predictor is treated as a variable, then we need to assume it is multivariate normal. Okay, so let's look at the figure, the graphical representation. This almost the same as the previous one, except now we add the xi as another predictor, another variable. So in this model, we have two variables, xi, the moderator, and also y. Okay, and then we also need to estimate the mean of the xi. Okay, and then its variance of xi. Okay, and if we look at the model implied mean structure, so we have two variables now. For the x part, for the y part is almost identical to the meta regression in the previous slide. But for the x part, we need to estimate mean, and then for the variance part, the variance structure, now it is a 2x2 covariance matrix. We also need to consider x as well. And one advantage of using the random X approach is we can define the explained variance with these functions. Okay, and then we can calculate the 95% confidence interval of these R squares using the LIGO-based CI. Okay. Okay, so now let's move on to more interesting application of these this SEM approach. Okay, and one question that cannot be easily done with the current SCM the current meta-analysis software is how to fit regression model or models with using the effect size as predictors. So in the literature, there are lots of applications. For example, we may want to, some researchers want to look at whether the effect sizes, the magnitude of effect sizes can help us to predict the number of citations. The basic idea is for studies with larger effect size, have more citations. Okay, so now the predictor is the effect size. And then the outcome variable, the dependent variable, is the number of citation, okay, which is the observed variables without sampling error. Okay, and there are other cases like in medical research. Sometimes they may want to use the baseline risk to predict the treatment benefit. Okay, and then in psychology, a recent application is to look at the effects of misinformation effects and then debugging effects. So the idea is to look at the beta naught, the intercept. So these intercepts, beta naught, the highlighted ones, represent the effects after controlling another effect size. Okay, so it looks like this is just a standard regression models. Okay, but among these three equations, they all have one problem. The effect size, yi, is used as predictor. Okay, so in the literature, we know when the effect size has different precisions based on the vi, if we treat them as observed, then the regression coefficients would be biased, and also the standard errors would also be biased. Okay, so in SCM, it's quite easy to address this concern. Okay, so now we have an observed effect size yi, and then we have another outcome variables. So for example, number of citation. Okay, and then we would like to use yi to predict it, but we don't use yi to predict it directly. Instead, we formulate latent variables of true effect size, the FYI here, this one, represent the true effect size without any sampling error. Okay, and then we have its heterogeneity, tau squares. And now we use this latent variable to predict the number of citation, beta 1. Okay, of course, we also have beta naught. Okay, so since we are not using yi to predict it, we are using a latent variables which is free of sampling error. Then the beta 1 is unbiased, and we can get the correct beta 1 and the correct R squares and all the correct statistical inferences is guaranteed by SCM theory. Okay, so it's very, so we don't need to derive new things. We just build on and take advantage of the SCM framework. As long as this one is a latent variable, the true effect size, then we can get everything correctly. Okay, then now we can take another direction to look at nonlinear models. Even though linear relationship is quite common and typical in meta-analysis, but there may be cases that we may want to fit nonlinear models. So either on the mean structure or on the variance structures. Okay, so here are some examples. So this is an examples to look at how the age and the effect size are related. So in this case, it looks like instead of using a piecewise regression, we can also consider as a smooth curve. Okay. Then another case is for the heterogeneity. It's quite clear when the moderator is more than the heterogeneity huge. When the value of moderator increases, then the heterogeneity decreases. Okay, so this would be problematic if we use the standard regression, the standard meta regression. Then one approach to address it is to use a location scale and nonlinear models. So in here, I just put them together because they're essentially the same. Nonlinear, when we fit nonlinear models or location scale, essentially we just treat the mean and the variance structure independently. So in here, for example, the standard location scale model, it breaks it down into the mean structure and also the variance structure. For the mean structure, maybe to make it a bit larger, for the mean structure, we can have a linear structure here. For example, we can use individualism to predict the effect size. Okay. For the variance structure, a standard practice is to use exponential function to ensure that the estimated heterogeneity is positive or at least non-zero. Okay. And now the alpha naught represent the heterogeneity variance when the xi is zero. Okay. And in here, as a demonstration, I use xi for both the mean and the variance structure. But in practice, based on your theory, researchers can propose different modulators for the mean structure and the variance structure separately. So there's no restriction what kind of models. Okay. So how to do it? And when we fit a nonlinear model and location scale model, it is quite tricky and difficult to frame it as a standard SEM model. Okay, because in standard SEM model, we are using the path loading, factor loadings to represent all this function, and it's difficult to do it. But in the SEM package or the function, it has a very nice function. Is we can define any arbitrary functions. Okay, so for example, here what we would like to do is first we define a standard something similar to random effects model. So for a random effects model, we have a mu, the average effect, okay, and then the VI, the non-sampling variance, and then the random effects, the heterogeneity tau squared. So in here, under this model, it is almost identical to a standard random effects model. Mu and tau squares, both of them are parameters. But what we would like to do is we are not treating the mu and tau square as parameters. We would like to treat them as outcome variables. So we use a double equal notation. In here, it represents the mu is defined as the beta naught, beta 1 times xi, and then the tau square is defined as the exponential of the alpha naught, alpha 1 xi. Okay. So what kind of model can we fit? It as long as they are valid R expressions, like the exponential power, then we can fit. Okay, so basically it's very flexible. Okay, so so by including these two lines, essentially we can fit lots of new models that we cannot fit under standard meta-analysis software. Okay, then the next step is essentially the same. We translate it into RAM representation. When we want to get the model-implied covariance matrix, we need to add a small argument here, replace constraints equals true. So what it means is after adding this one, then internally the function will replace the mu and tau squares with this expression. And then if the parameter like beta naught, beta 1, alpha naught, alpha 1 haven't been defined yet, then automatically define these parameters. Okay. Then when we feed it to our data, then we can also need to add this replace constraints. Okay. So after fitting it, then we get some standard results like the alpha naught, beta alpha 1, beta naught, beta 1, the estimate, the stat error, lower bound, upper bound. Okay. So sometimes when we have difficulties in fitting some nonlinear models, then these functions can also allow us to provide our own starting values. Okay. Okay. So so essentially we can fit lots of nonlinear models on the mean, on the covariance structure or variance structure, depending on our hypothesis. Okay, so now let's move on to a slightly more complicated case. We may have more than one effect size, for example, bivariate meta-analysis. But essentially, it's almost the same as the the random effects model. So this is a standard random effects model with two effect sizes. We have yi, the first effect, y2, the second effect size, and then the mean average effects, mu1, mu2. Okay, and then we also have the known sampling variances data. Now we got VII because V is a 2x2 covariance matrix, and then we have the V22. At the same time, we also have the known covariance V21. Okay, and then we also have the random effects U1 and U2, and then this heterogeneity to tau consists of 2x2 covariance matrix. So this is a standard one. So nothing special. But just in terms of notation, we need to double the to write the code a little bit longer when we have two effect sizes. Okay. Now, this SEM approach can also help us to entertain some interesting scenarios when we conduct a multivariate meta-analysis. One common problem is it's difficult to find the known or to the correlations between the effect sizes, but we need the sampling correlation between them in order to calculate the V21. Okay, there are a couple of strategies how to address it. For example, we can find we can estimate the correlations based on other literature or handbook or other sources, or we can do a sensitivity analysis by you trying, let's say, the correlation varies from 0.3 to 0.8. Okay. And Riley proposed a model that assumes the between and the within study correlations are identical. And we can fit a model with similar ideas. Okay, so now instead of using one, we standardize all the sampling variances and random effects. So now probably you notice all of them, the variances are one, meaning they're all standardized. Okay, and then the standard deviations or the standard error are represented by the factor loadings here. Okay, now that this is the correlations between the random effect, the between random effect, and this is the correlation of the within studies. Okay, and since we are using the same notation rule, then we assume the between and the within are identical. So now we can fit a model, and then we can estimate the correlation, and assuming the between and within would be identical. Of course, its performance depends on whether the within is really close to the between. Let's say if the within is positive, but the between is negative, then by fixing them to be identical, then the estimates would be problematic. But if they're quite close, 0.3, 0.4 in this magnitude, both of them are quite similar, then we expect it may perform quite well. But the idea here is not going to say whether this is a good model, but it just allows us to have different lots of possibilities by using this framework. Okay, to summarize, this SEM-based meta-analysis has several strengths. For example, it helps us to understand and learn meta-analysis using graphical models. And it helps us to derive the model-implied means and covariance structures symbolically. And more importantly, it helps us to fit the model to our data. And there are also some byproduct advantages. For example, we can impose linear, nonlinear constraint on the parameters. We can define new functions or parameters like R squares indirect effect, and then we can get the confidence interval with LIGO base. Then we can handle missing data with full information maximum likelihood. And if we are interested to MESEM, in fact, this approach can be used to fit one-stage MESEM. Okay, so in the preprint, I have an example to demonstrate how to use this approach to fit a one-stage MESEM. But it's not as good. The results are identical, but in terms of writing, in terms of the code, it's a bit long. So I mean, personally, just for fun. So it just try to demonstrate the the flexibility of this approach, if you're going to fit metaSEM, I would strongly recommend you to use the metaSEM functions instead of using this approach. That said, there are also a couple of limitations. For example, if this data mainly use full information maximum likelihood, if you want to use other estimators like weighted or unweighted methods of moment, then it's almost impossible to implement them under the SEM framework. And currently, in SEM, it relies on the z-test or what-test instead of t-test. But this can be fixed quite easily if you do some manual fix. And lastly, we still need to implement the three-level meta-analysis and more importantly, robust variance estimation. So if it can be used to implement the robust variance estimation, then it will be a very powerful framework to fit various models. So to summarize, I hope these short presentations can give you some ideas what kind of SEM-based meta-analysis is. And its whole idea is we can use it to fit some novel models that haven't been available yet, especially if you are interested in fitting, let's say, models, mediation models with various effect sizes. And there's a preprint available related to this topic. And then the R code, if you're interested to check it, in this preprint and the R code, it includes more than 20 models with examples of all of the univariate, multivariate, and then the metaSEM. Okay, so I'll stop here and thank you for your attention. And now I hope to get some comments, questions, and please feel free to raise any questions you have. Any questions, or you have no idea what's it about?
I think Jingru has a question in the chat about do
Okay.
we need identification rules for meta-SEM as those in traditional SEM? Jingru, do you want to explain a little?
Yeah, thanks, Cheung. Hi, Dr. Chen. I wonder
Hi.
if we need to consider any model identification rules in meta-SEM as traditional SEM.
You mean the identification rule in metaSEM? So what kind of so the metaSEM essentially is the same as the standard SEM. So the model would be exactly the same. So in other words, if you have problems in identifying your model in SEM, then your model won't be identified in metaSEM. So do you have any specific example? Why is concerned?
Currently, I don't have a specific example, but I recalled previously when I have an SEM course, there are several identification rules that tell us whether the model will be identified or not.
I see. Okay, so first of all, let's classify under two types of models. The first one is path models. If you only have observed variables, there's no latent variables at all, then there'll be almost no concern on identification issues. Okay, so you just fit a path model with mediation of multiple mediators or regression models. Then identification is not a concern. Okay, so it's only a concern when you have latent variables. So let's say if you're fitting a confirmatory factor analytic models, then the standard practice is for each latent variable, you need to fix at least one indicator, either fixing the variance at 1 or fixing one loading at 1. In metaSEM, usually we are using a correlation matrix. Then by default, we are fixing the factor loading. We are fixing the factor variance at 1. Then we free all the loadings. Then the identification issues would not be a concern. So essentially what it means is if you are fitting a latent variable with 3 latent factors, then all of these 3 latent factors, we fix their variances at 1, then problem solved.
Cool. Thank you so much.
Thank you.
Thank you. So there's another question in the chat from Taraka. Sorry if I pronounce it wrongly. Taraka said, what about the conditional independent claims? For example, the D-separation claims in the SEM. Does the MA-SEM model also check for them as in the standardized SEM?
Can you elaborate a bit about this conditional claim? Because let's say, as I said, if you're fitting standard model, then usually it's not a concern. Usually, this separation is more like you are trying to draw causal conclusion to see whether the conditional variables are still correlated. So the MESEM essentially is the same as the. So one important thing I'd like to clarify is MESEM is not something different from SEM. So the idea why I like to work with MESEM or to bring the meta-analysis into SEM framework is it follows all the SEM theories. So essentially, I don't need to justify why it works, how it works, because it's a standard SEM model. So if the only difference is the estimation method. For example, if you in standard SEM, usually we use maximum likelihood, but in MESEM, depending on one stage or two stage. For the two-stage approach, when we fit the model, we are using a weighted least square. But the estimation method does not affect how the model is identified or the whether it's valid. So essentially, if you are going to fit MESEM, then if you have a SEM background, then it helps a lot because it's exactly the same as what SEM you have learned in the textbook. Okay, any other questions or comments?
Hi, Prof. Mike.
Yeah.
That means like we get estimate like chi-square value, like test whether the model agree with our SCM. Do we get such measures in this output as well?
Yes. So you mean the R squares?
Chi-square.
Chi-square. You mean the chi-squares?
Yes.
Or R square?
Chi-square.
Yeah. So we also have the chi-squares. So but just to clarify, so it's not directly related to the SEM-based meta-analysis I'm talking about today, because in this case, the chi-squares difference test is used when we're fitting a model against the data and see if the model fits the data. So in here, if you're fitting a model like this, then we don't have the chi-squares. We don't have the log likelihood, okay, because there's no need to do it. But in the MESEM, then yeah, sure, we have the chi-squares, all standard output like the chi-square, RMSCA, CFI. They're almost identical to standard SEM. Yeah, James.
Like that, I really appreciated the example you showed where you're doing a latent regression of one effect size on another. This is something that's been coming up a lot for me lately. I don't know why, but it is very interesting. I think it's a very compelling use case. I'm wondering if you know anything about the performance of doing this in an SEM framework versus doing something more ad hoc or like ham-fisted. Like I've tried to do something similar to this in Metaphor, where you just get the covariance matrix of the random effects and then kind of do the regression for yourself off of the covariance matrix and then either just delta method or bootstrap the standard errors. Do you know anything about like, whether the ad hoc stuff works, or like is the SEM approach really a lot better?
I don't know there's any study. The main interest for me, especially when I was preparing the preprint for this talk, for this whole idea, was to prepare a tutorial to demonstrate how SEM can be done. So then now the tool is available. So now if anyone who would like to investigate the idea, if you just use the effect size as a predictor versus the so-called the more proper SEM framework, is it really has an advantage? Then I think they can do the simulation quite easily, because now there's a tool to do it. Instead of you need to write a very difficult function, lots of our code to do it. It just, I think, less than probably 5 or 10 lines of code. Okay, so you're right. There are lots of interesting things we can test, like to use the observed effect size versus the latent effect size. Or by the way, when I check this one, there are some interesting things we can also check. For example, I've also tried to fit a model with the observed effect size as a predictor to do it. So this is a more like an ad hoc way. Then I can also calculate the model-implied covariance matrix. Then we can compare the so-called the theoretical correct one like this one versus the incorrect one, and then we can see what are the differences. Secondly, it's not only the beta, it's also the R squares. Okay, because the R squares in this so-called the correct one, let's assume it is correct theoretically. The R squares, when we calculate the variance of the effect size, is based on the true tau squares and not the observed y. Okay, so it means this not only affecting the beta one, it also affects the R squares. Okay, so at least I think for future investigation, then we can look at both the beta one, the regression coefficient, and also R squares. So theoretically, I would expect if we use the observed effect size as predictor, it will bias both the beta and R squares. Is it true, or how large the effect is? Then we need to do some simulation, or some student, potentially good topic for master. So I think for this one could be good enough for master thesis to investigate a small part like this, then compare. And another factor probably will also affect it is the VI. How large is it? Is it more or less the same across all studies? So if they are all similar, for example, the N more or less the same across all studies, then I would expect probably the effect would be smaller. But if we have very large VI and very small VI in the same data set, then the impact probably would be larger. Okay, so potential topic for students.
Yeah, there you go, folks. Dr. Cheung's writing your dissertation for you.
Yeah, there are lots of interesting ideas, and I don't think I have time to investigate all of them. And I'm happy to provide some tools so that users or others can use the tools to address research questions. That's my main objective of this tutorial. And in fact, there's nothing new from SEM perspectives, but I think when we combine meta-analysis into SEM using this framework and using OpenMX and lavaan, then it will be a very powerful tool for us to address research question, and then it will lower the bar for the students or researchers. They don't need to write lots of R codes in order to fit a model. Any other questions I have missed?
I know we're right at time. So say last call. Okay, maybe we're good. Thank you once again, Dr. Cheung, for this presentation. It's really great to get a tour of this very powerful software and see the connections between SEM and familiar meta-analytic models. We'll be back next month on November 15th. Dr. Mikkel Vembje from the Danish Center for Social Sciences is going to be presenting on using GPT models, so like large language models, as second screeners of titles and abstracts in systematic reviews. So we'll be sharing more details about that talk through our mailing list and social media, so keep an eye out for it. Thank you all for coming, and we'll see you soon.
Thank you. Okay, bye.